In this video, we're going to look at a specific use for exponential functions, and that is to compound interest or calculate compounding interest. So if you have a savings account and they offer you any rate of change, basically they're paying you a little bit every month for using your money. And how they tend to do this is they say, I'll give you a percentage of what you already have in here. Well, when we talk about exponential growth and decay, that fits really, really appropriately because we're always taking some initial amount and multiplying it again and again and again and again by some base. Okay, so that repetitive multiplication there can be interpreted as being some sort of interest being compounded over time. So before we get into our compound interest here, we're going to first introduce a new constant for you here, and this is our natural base E, and I'm going to put quotations around this because this is what we call this. We call this the natural base. We say that it is the number E because it's named after a Swiss mathematician. Leonhard Euler is how you say his name, but it was his number that he kind of discovered here, and it's pretty profound. We refer to this as our natural base, and I'm not kidding you, it is the most important base for exponential functions. So that is to say that when we write functions like this, you're going to see there's a whole heck of a lot of times where we have a base of E, and that's totally cool. So you heard me mention to this as being a number. Let's talk about what it is. We say E is an irrational number, which means we can't write its exact value, and then it's approximately 2.718281, and it goes on forever and never repeats. So first thing I want to do is I want to have you grab your calculator because we want to find where this E key is, and I'm going to tell you it's always behind your ln key or your natural log key. So if I were to type in, for instance here, E to the 1 power, what might this maybe look like here? I would get about this 2.718281828, and trust me, it doesn't repeat. It goes on forever and ever and doesn't repeat. This is some really weird irrational number, but it does exist, and it is some positive number that's not equal to 1, so we can get away with using it as a base on our exponential functions here. Okay, so let's go ahead then and take a look at our compounding interest formulas here. And there are two of them that you're going to need to know. The first one I'll point out is actually the one for continuously compounding interest. And so the reason why I want to point this out is just because it has our base of E, and it is the more elegant of the two formulas. We say that A equals PE to the RT. Now, usually we don't write things this way as a function. We tend to write them as this: y equals PE to the RX. And in this particular instance, what I want you to notice that is our capital A value here, or some amount, that's really representing our Y value. So I'm going to say A is the amount, but we're going to say amount at time T. Okay, so if you give me a time, I can tell you the amount of something. You would have to tell me some other things first. And so, like, what else would you have to tell me? The principal amount. And what we want to say is this is really just our initial amount. We're also going to make one more amendment here. We're going to say amount at time equals 0. That is to say that when we look at this, at least in a graphical sense, when we say x is our time variable and y is our amount, we're going to say that this always represents kind of like our y-intercept. And so I want to make sure that we include this also. Our p value there is our y-intercept, graphically speaking, or just what you started with. So our principal amount. R is a rate. What you're going to want to write for your rate here is must be a decimal. So if you remember your rules for switching from percentages to decimals, for instance, if my rate is 5%, we have to take the decimal on this number and shift it twice to the left. That would be the same as 0.05. These mean the same thing, but in different forms. And then T is going to be our time, and it's usually given in years, but it doesn't have to be. It could be given in seconds, minutes, microseconds, whatever you want for your particular experiment here. But essentially what I want to point out is this time variable, this T right here, is really just like our X, okay? So we're going to say that this is our X variable here, whereas our amount is kind of like our Y variable there. So I'm going to write time and amount, and really what we're doing is trying to give the amount of something at a given time modeled by these equations here. So now that we've looked at our continuously compounding interest, let's take a look at our compounds n times per year. And the very first thing I want to kind of hit on is this: n times per year. What does that mean? It means that maybe once a month the bank likes to do that thing where they give you a percentage of what you already have. And so in terms of n times per year, if they're going to do that for me every month, once a month, that's kind of like saying I'm going to do it 12 times a year. And if they did it daily, we would do it 365.248 times a year. Or if they did it weekly, we do it 52 times a year. So looking at this formula, I'm going to rewrite this here. We're going to say A is equal to P times, I just want to clean this up a little bit, R over N to the N times T, where all of our values are still kind of representing the same things. This is some amount at a given time, and I can tell you that amount at a given time if you tell me some other things first, like what was the principal amount, the starting amount, what's your rate R, and what's the time t. The only new thing here is that there's this n that's involved here, or n is the number of times per year that it compounds. Okay, so really quickly here, notes on n compoundings. Okay, you're going to see some vocabulary. So you're going to hear things like it compounds annually. What would that mean here? Annually. Okay, I suppose that would mean n equals 1 time a year. Whereas if I say semi-annually, that would be twice a year, just because it's happening every 6 months. If I say monthly, we're going to acknowledge that this means that n is 12. And if I say daily, okay, daily, we get n is equal to, and we're just going to go 365. So you might hear some weird ones. You might hear like biannually. I'll just throw this one out there just because it's a really weird case. But biannually would mean once every 2 years, which would mean how many times a year? 0.5 times a year, which is crazy. But just know that n represents the number of compoundings per year. So the difference between these two models is that in the first model, we actually know how many times per year it compounds. And in the second model, we assume that it's compounding every moment of every day. And it becomes this a little bit more elegant form of this formula here. So we're going to put these two formulas to use, and we're just going to model some growth here on this $12,000. So it says a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly or continuously here. So first things first, when this says quarterly, that's a key indicator that I'm going to be using this first formula. I'm going to go ahead and write that down. We say the amount at any given time t is equal to what you started with times 1 plus the rate over the number of compoundings per year to the power of number of compoundings per year times the number of years. So some things that I tend to recommend to people are write some stuff out. Like, what is P? Well, we know P is $12,000. We know the rate here. The rate is 9%. So remember that we have to write this as a decimal, 0.09. And this is compounded quarterly, which means 4 times a year. Okay. I suppose the only thing that we're missing here is the time. And in this case, we say that the time is given to be 5 years. So I'm going to sneak that in here. T equals 5 years. And I suppose that what I want you to do for yourselves is just fall into this habit of forming a table here. We say at a given time, what's the amount that I have? Okay. So we're kind of investigating what's the amount I'm going to have at 5 years. We're just going to fill this out, and I'm going to try to write smaller here. We're going to say 12,000, okay, times 1 plus 0.09 over 4, so our rate over number of compoundings, and I'm going to slide across here, give us a little bit more room, and this is to the power of n times t, where we have 4 times a year for 5 years is 20 overall times this is going to compound. Anybody that puts this on their paper is like totally 100% right. I got to give you credit. The only thing is, like, if you tell me that's my bank statement balance, I'm going to be a little upset with you for giving it to me in that form. So this is the part where we're going to go grab our calculators, and we're going to make sure that we can craft this statement carefully, but all at once. Okay, so we have 12,000, and this is just going to mean we're going to have to use our parentheses wisely here. We have 1 plus 0.09 divided by 4. Now notice on the inside here, I didn't put parentheses around this fraction because on the inside of my parentheses, my calculator is going to do the division before it does this addition, so we can get away with it. But we say this is to the power of, now I do need parentheses around my exponent because I do need it to do the 4 times 5 before it raises this base to that power. If I hit enter, what I see is that in 5 years at a 9% rate, dude, I've made like $6,726. So we have $18,726. So we get about approximately $18,726. And because this is a monetary value, we're going to go with about 11 cents here. If I can get back to my screen, 11 cents. Okay. So now let's look at the difference between that and continuously compounding. And the cool difference is that we collapse to this natural base E. If you compound forever and ever and ever and ever and ever, all of this 1 plus R over n to the nt business just becomes E to the RT, which is really cool. And in this instance, what I want you to notice is that we have the same $12,000 that we started with here. We still have the same 9% rate that we started with here. It's just that our n is continuously compounding. So we don't have an n here. Our time is 5. We're going to build a table, as we do. We're going to say time and amount, but this time when we put in 5, I have to say, well, I started with $12,000, and this is times e to the rate, so the rate is 0.0. I'm going to try to write that a little bit bigger. 0.09 times the time, which is 5. This is a little bit easier to type into our calculators this time. And so, again, remember that we have to go get our E button out from behind our natural log key, our ln key, but we say second ln, and we're going to go 0.09 times 5, which is our time here, end parenthesis, and hit enter. And you'll notice that we actually make a little bit more money compounding continuously than you do just 4 times a year, which would make reasonable sense given that the more you compound your money, the more you're building on it. Okay, so we get about 18819. So we get about 18819, and that was out to the nearest hundredth here, about 0.75. So 75 here, this would be the amount we would have after 5 years, as opposed to the amount we had after 5 years compounding quarterly. So just know what these formulas are, know the difference between when to use them and how to use a calculator to get your answers here. Cheers.